Hi, my name is José Aguilar, and my research project is called Advanced Control System to Improve Durability and Efficiency of Fuel Cells in Autonomous Mobile Vehicles. My supervisors are Dr. Attila Husar and Dr. Juan Andrade. The transition to a clean economy requires the combination of sustainable energy sources with the efficient conversion, transport, and storage of that energy. Hydrogen is an excellent candidate as the energy vector of the future. In this context, fuel cells will become the main device for energy conversions. Fuel cells have a large energy-to-weight ratio, and in combination with a battery in a hybrid system, they overcome most of the other electrical technologies. Fuel cells have many advantages that makes them a great alternative for powering mobile vehicles. However, there are still several challenges to be solved, such as low durability and high sensitivity to load changes. My research focuses on addressing these issues. Let's see how a proton exchange membrane fuel cell works. The cell is fed with hydrogen in the anode and oxygen in the cathode. In the anode catalyst layer, hydrogen breaks into electrons and protons. Electrons go by an external circuit and protons travel through the membrane. In the cathode catalyst layers, proton, electrons, and oxygen combine to form water and release heat. The catalyst layer formed by platinum-coated carbon is a fundamental part in this process, and also one of the most sensitive elements. The platinum, which is a rather expensive element, suffers high degradation when the cell is not working under appropriate operating conditions. This degradation results in voltage decay, low efficiency, and shorter useful life. Operating conditions have a fundamental impact on the integrity of a fuel cell. Different values of temperature and humidity change the ratio of dissolution of the platinum in the catalyst layer. Also, different load profiles produce different patterns of platinum oxidation. In order to tackle these challenges, we propose a novel integrated control and motion planning architecture. A proton exchange membrane fuel cell is the power core of the system. Also, we have several subsystems needed to regulate the operating conditions of the cell. At the top of the architecture, there's a high-level controller that will generate optimum set points of the operating conditions for the low-level controllers of the subsystems. The motion planning module of the robot will interact with the fuel cell controller in order to plan optimum robot motions with the objective of improving durability and efficiency of the whole system. Hybridization is done by adding a small battery and an energy management system to control power flow. Summarizing, the goal of the research is to build control-oriented models of cell degradation and then use these models to optimize the operating environment of the fuel cell. The idea is to define optimum operating values of temperature and humidity in real time, and also to include the motion planning capacity of the vehicle to solve the problem of non-optimal load profiles. We have presented our current results in several conferences and submitted for journal publication. Thank you.